I'm Professor Austin, and I'm giving the keynote I gave at Micro last month. I gave the keynote at the Micro Symposium in Hawaii. This is it's the exact same talk, so I'm just giving it again. And we're recording it. I wanted to get a recording of it for posterity purposes. So I think it's okay. I think I want to. If people want to ask questions, go ahead. Otherwise, you can ask questions at the end. But I think it's okay to ask questions during this thing. Title is Preparing for a Post-Moore's Law World. This talk is about what are the implications to computer architecture when Moore's Law ends, which is, as I'll show you in this talk, is happening right now. Moore's Law is important because it's the primary means that we scale power, performance, cost in computing systems, and that scaling is the value that we create as architects, what we sell when we design a computer. This talk is all about how do we continue that scaling once Moore's Law ends, and how do I get a perspective on that? In 2013, I got awarded a very large center here at University of Michigan. We've got 27 faculty from 14 universities. We support over 90 students. And for the first time in my career, I had to stop thinking just about my research and think more broadly about the research of the community. And that really led me to these topics that I'm talking about today. So I'm going to talk about the problem, but I'm also going to talk about solutions to the problem. And strangely, not all of them come from the architecture world. In fact, probably the most powerful solutions come from the CAD EDA world, as I'll talk about later. So CFAR is the center that I had that focuses on this problem of scaling. The goal of the center is really to serve tomorrow's applications. Things like computer vision, machine learning, big data analytics. There's lots of algorithms out there or applications out there that can use scaled systems. But the big challenge is, how do we innovate in a way that's effectively scaling? And how do we do that when silicon is really losing its value? We'll talk about that. And then how do we do that on top of silicon that's even becoming unreliable today? So there's a lot of great challenges. Makes for a very interesting time in computer architecture. And then I'll just say, I won't mention it over and over again, but all the work in this talk is work from CFAR faculty. Now, all keynotes, all architecture keynotes, by union rules, must start with Moore's Law graph. And it's a good idea to start with a Moore's Law graph because Moore's Law is the fuel that drives the engine of the computing industry. What is Moore's Law? Moore's Law is this 2x density every 18 months, this green line here. Over decades, we've seen by shrinking transistors, we get double the density for the same cost roughly every 18 months. And with that, for a long time, we saw this, this blue line here, this purple line. We saw that the speed of the circuits increased in a similar manner, as well as their power scaling, their power density, as well as instruction level parallelism. But around 2000 to 2005, you can see these three performance aspects started to drop off, even though the density scaling continued on. When the frequency topped off about 2005, the impact there was a lack of perceived value in uniprocessors. Today, uniprocessors are not, we don't even sell uniprocessors today anymore. And when the power density scaling stopped, that was the start of dark silicon. I'll talk about that in a little bit. And then finally, when the ILP topped out, that was really when we had to move away from microarchitecture and start looking at system architecture as a means to create scalable systems. A key number I want you to see here is if we draw this line out and look at what the gap is today, it's about 10x. Had the performance metrics continued to scale with density for the last 10 years, our uniprocessors would be 10 times faster or use 1/10 the power. So that gap is what we need to bridge somehow if we want to continue to create value in the form of scalability. Now, normally people, when they show this graph, they go, but isn't it beautiful that density keeps scaling? We've got more transistors, but I'll show you on this graph that Moore's law is ending, and it's ending right now. Here we see a log scale of density of dimensions, minimum transistor dimensions, from 180 to 130, 90, 65, 32, 22, 14. That's the current advanced node today. These are Intel technology. And on the bottom here, I've got the street date when Intel first sells that transistor. That's when they appear. That's when you can buy them. And so I've taken 4 generations here, 180 to 45. I drew this gray line here, and then I extended it with the red line. That's actually Moore's law scalability. That's 2x every 18 months. But if you look from 45 to 14 and then extend that line out, you'll see we've moved from Moore's law to Moore's crawl, 2x every 36 months. And recently, Intel announced there was a 5 or 6 quarter slip in 10 nanometer, which is going to take us to even a slower increase in density. Now, Moore's law never really stops. It slows down, and it doesn't become exponential anymore. It becomes linear. And the transformation that'll happen here is from one of density scaling to innovation on the technology device material side. So for example, we saw a recent advance like in the form of FinFETs, where by changing the geometry of the transistors, we get an advancement. And now there's the PinFETs coming, and there's better material and lots of things. But what we'll see is that we won't get the 2x devices every 18 months ever again. We're going to get incremental increases in the future in our silicon. Now, will we switch over to non-silicon? Unlikely. The investment in silicon is too great. Will there be non-silicon devices integrated? Perhaps. But again, those aren't going to provide the scalability that silicon has over the last 40 years. Those are still made out of atoms. And we're really at the atomic density here. At 7 nanometers, you're talking only 14 atoms in the width of a minimum size transistor. It's just not a lot further down you can go from there. So what do? We're losing all of these benefits that architects have been lavished with over decades. Now, just to recap, value, the thing that you make money on when you sell to a customer, has always been scalability in our community. Faster computers, lower power computers, cheaper computers. And we're losing the technology scaling side, density, power density, as well as transistor speed. We're losing all those things. So what does that mean? It means to architects, you got to innovate or you're going to die. Now, what does it mean when a community dies? It means the community isn't very important anymore. Nobody really cares about it. Students don't go into it. People don't invest in it. There's no startups in that community. We're already seeing this happen in the hardware community today. I'll show some of that in this talk. Our community is dying because we're not able to fill that gap with innovation. So the goal of this talk is really to talk about how do we restart this innovation and make it happen more quickly, more efficiently. All right. Well, architects are a nimble bunch, and when we first found out that we weren't going to be able to scale at the uniprocessor level, the solution that came about was the chip multiprocessor. So let's take a look at the chip multiprocessor. We're 10 years down the road. Let's do an assessment. How well has it done? So chip multiprocessor, we're going to put multiple similar cores. It's a homogeneous parallel architecture. These are the same cores communicating through some shared infrastructure, some shared memory system. There's a great paper. I recommend everybody read it by Hadi Azmazelzadeh. and Georgia Tech. This is when he was a grad student at UT Austin, where it's dark silicon and the end of the multi-core scaling, where they did a study in this paper where they looked at homogeneous parallel architectures, and they scaled them over time, accounting for both technology advances, architectural advances, and application advances. And they did this for the parsec benchmarks, which are very parallel benchmarks. So there's really sort of a best case scenario in terms of the software you're running on it. And this green line is Moore's law scalability over time. So we'd want our homogeneous parallel systems to follow that line if they were able to deliver scalability that would help close that gap. But what they found is that they were able to get 13% more performance every 18 months for a variety of reasons, which we're kind of tease out now. One of which is dark silicon, but there's many other problems as well. So, on the technology side, it doesn't look like homogeneous parallelism can really save us. I think it's also interesting to look, because we create value and try to sell that value, I think it's also important for us to look at how does the press and the public see the value of our work. So I went to Google and I typed in, "Are computers getting faster?" And this is what I found. Why CPUs aren't getting any faster? Moore's law isn't making chips cheaper anymore. Are new laptops really faster? As it turns out, not really. Do I even care about fast processors anymore? And then one of my colleagues, Valery Bertacco, said, well, that's a kind of a negative question. Why don't you put in a more positive question into Google and see if you can get a better result? So I typed in, computers are getting really fast. And here's what I got. The death of CPU scaling from one core to many and why we're still stuck. Why aren't processors getting faster? And then finally, a glimmer of hope. How fast does your PC really need to be? Maybe we don't need performance. I disagree with that assessment. But the perception of what we're doing is very poor. I think we can all agree on that from the public. So who's to blame? Who's to blame for the ineffectiveness of chip multi-core computing as a means to innovate our way back to Moore's law scalability? Well, some people say, blame the programmer. But I say, nay, we can't blame the programmer. Why? Because programmers are very good at extracting parallelism. And where there's a desire to have parallelism, they've done a fantastic job. So there's niches where parallelism is aplenty, and we're still not getting the scalability we want. Here's an example of one, Bitcoin mining. This is a 2,000 square foot warehouse, just contains GPUs. It does 1 petahash per second, reportedly generates 8 million Bitcoins per month. And there's many other things that you can look at. Warehouse scale computing, another space where you've seen parallelism really take off. By the way, warehouse scale computing, that is what a testament to the poor work of the architects, in that instead of scaling on the chip, they scale out of the chip. And they say, we don't care what's on the chip. We just want to build our own big, massive parallel computers. And they program them very effectively. So I say, no, programmers are doing a great job. So then people say, well, let's blame the educators. This is the guy that taught me parallel programming. This is Jim Goodman from University of Wisconsin. Let's blame the educators. And I say, nay again. CS is booming. Booming. Everybody wants to be in CS. It's the fastest growing area in the university here at Michigan. Here you can see CS enrollment over time. It's really on its own Moore's law trajectory. I mean, we meet every semester to try and figure out how we're going to handle all these students. Oh, these two lines? EE and CE. More about this later, but you can see that the hardware side is very flat over a long period of time. And we've got lots of classes at Michigan that teach parallel programming, both the undergrads and the graduate students. So there's a lot of opportunity to learn about parallel programming. And people that know me know I've been working in Ethiopia since 2009. Even there, second most popular degree in the university is the CS degrees. First most popular civil engineering, because there's a huge infrastructure boom in the country, so there's lots of jobs in that space. But the world over, we're making lots of programmers, and we're teaching them how to do parallel programming. So it's not really a programmer. I don't think we can blame our educators. They're producing the good programmers. So, well, maybe the transistor is to blame. And I will say, yay, the transistor is definitely to blame. Let's see why. These are some slides from Michael Taylor at UCSD explaining the problem of dark silicon, which has to do with transistors, when they get smaller today, don't use less power at the rate they used to use less power. So consequently, if we can't scale the amount of energy we shove into the chip, we need to turn on fewer transistors. And that's the dark silicon problem. Traditionally, when you would scale 2x in density, that means that the dimensions got divided by 1.44 in both dimensions, you would have roughly 2 times as many transistors, and then each of them would be about 1.4 times faster because it was smaller, had less charge, responded more quickly. About a 3x improvement in computational performance per unit area. Well, if they all use the same amount of power, we'd have to have 3 times as much power going on chip. So instead of 3 amps, you'd have to have 9 amps. And, and these chips, the technologies for bringing more power on chip have advanced at the slowest rate you could possibly imagine. But fortunately, because of Dennard scaling, there's Dennard there, he noted that if they're running faster because they're smaller, they're also using a similar less amount of power because they're smaller, because there's less charge in their channels. And then here was the kicker. We could make up the rest by dropping voltage by a factor of 1.44. If you drop voltage by a factor of 1.44, you cut the amount of energy going on chip in half, and you got back to the original point. We had 3 times as much computational power at the same amount of energy going in. But then something happened with this guy right here, the dielectrics. The dielectrics between the gate and the channel got so thin that in order to lower VDD, to do this step right here, we had to lower the threshold voltage. And the way you lower threshold voltage is you make that thinner. And that got so thin that the leakage started to spike up. So now, if we drop threshold voltage, leakage goes up. So your dynamic is still scaling down, but your leakage is shooting up, and you still need more energy to go on chip. You've lost this component. And the only way we can deal with this is by turning off a larger fraction of transistors every generation. And that's not a good solution for chip multiprocessors. Chip multiprocessors need everything running all the time. So this really flies in the face of that particular design. So yeah, transistor, you are letting us down big time. But I say there's one other person to blame. The architects. Do you recognize that guy? That's Gene Amdal. In '65, when I was born, this guy started talking about Amdal's law. He didn't call it Amdal's law, but he talked about how as we expose parallelism, we'll get so good at it that eventually it won't be useful at all, because the performance of the program will be determined by the parts that we didn't parallelize. Now remember that number I had earlier in the talk, the 10x? Where does 10x place us in terms of Amdal's law? What do we have to accomplish? 10x puts us right about here. It says that if you want 10x performance improvement with homogeneous parallel chip multiprocessors, you need to parallelize 90% of the execution. And you need to run it on upwards of 1,000 processors. That's how you get 10x. That seems like a pretty ridiculously hard goal for a parallel system. And oh, by the way, in 18 months, you're going to have to do 95% on 4,000 processors. Okay, so it's not a sustainable scalability approach to rely solely on parallelism. We don't want to throw away parallelism. It's a great way to provide speed ups, but it is not a solution to Moore's law scalability gap. It's only a part of the puzzle. So yeah, architects, we really should have known back in the 60s that homogeneous parallel architectures weren't going to save our bacon. So what is the solution? What do we need to concentrate on? And I say the solution is this guy right here. Well, not this guy actually, but the research this guy did. This is Jason Clemens. He was one of my PhD students. And he did research on how do you accelerate the performance of computer vision algorithms on embedded hardware, which is a really difficult problem because computer vision is a very computationally intensive algorithm. And when you say you want to do it on an embedded platform, then you're not only worried about performance, you also want to do it with energy efficiency. It's kind of the worst possible scenario to deliver that. And so Jason and I started working together on this problem, and we soon figured out that we really need help in the application space because the vision algorithms it's a very broad space that draws from image processing, from machine learning, and also from computer vision. They have their own host of algorithms. So we started working also with Silvio Savarese, and Jason, I told him, when people ask you, are you an architect? Say yes. When they ask you, are you a computer vision researcher? Say yes. You got to really have both those things. And what he did is he built an architecture that was tailored to the particular space. It was a heterogeneous parallel architecture. It was a parallel architecture that was customized to do well on the serial components that were left over after you parallelized. This was the magna opus of his thesis, which was the EVA architecture, the embedded vision architecture. And I'll just give you 3 things that it does that provides a lot of value because it understands the vision application space. For one thing, it's a heterogeneous multi-core. So it's composed of a couple big powerful cores that are serving stuff to a lot of very small cores. In that environment, you can expose a lot of parallelism, and if you can tease out which threads need capable cores versus simple cores, you can do an assignment and you can get more performance per energy, more performance per area, which is also important in the embedded space. Second thing it had application-specific functional units, monopoly compare, dot product unit, vector max, decision tree compare, simple little accelerators that could be applied across a large number of algorithms and provide very good speed up by simply reducing the latency of some of these long non-parallel kernels. And then finally, one of the things he did is he taught the memory system how to do really well at a style of algorithm called a stencil. A stencil is an algorithm that doesn't deal with a data element. It deals with a region, a two-dimensional region of data. And in fact, these particular algorithms tend to have a velocity vector associated with that. And so you can do a really good job of doing two-dimensional prefetching to increase spatial locality significantly. That lowers energy as well as improves performance of the memory system. So there's 3 examples of how you can serve this space. But here's the thing that I really want to leave you here. He found a 90x greater efficiency over an embedded CPU. So 90x efficiency. Efficiency means he did less work by a factor of 90. He can spend that either in performance improvement or in energy savings or anything in between. But you'll note he got that 10x gap closed and then he went 9x past it. And that was just pure innovation. Innovation that combined parallelism with customization for a particular application space. So where we need to focus as a community now is on heterogeneous parallel architectures. We need to embrace parallelism. Parallelism is a good thing. And we need to embrace customization. Customization is a good thing. But for the first time, we really need to start being serious about bringing those 2 things that normally don't fit well together in tandem. Because those heterogeneous parallel systems, they overcome dark silicon because they concentrate computation to the smallest component possible. I don't need all my transistors working at the same time. And they overcome the tyranny of Amdal's law because where there is serial aspects of my program, I can apply acceleration to those things. Now, normally in a talk like this, I would spend the rest of the talk telling you what are good ways to do heterogeneous parallel design. But there's a little twist in the middle of this talk because I'm not going to do that. Why? Because I know architects are smart and they're going to figure all this stuff out. In fact, it's not that interesting to me to know how to do this for all the different applications that are out there. People will figure that out. It's not that hard. And the results are really good. And for decades, we've seen that the results when you specialize for an application are really good. What I want to do now is I want to tell you why there's a good chance that this will probably never happen. And to understand that, you need to understand what I like to call the good, the bad, and the ugly of today's silicon. First, the good. We saw the good. Heteroparallel systems, they can close Moore's law gap. You can get 10, 50, 100x out of those architectures. And I know this community can build those architectures. Those designs will exist. Here's the bad. We're losing Dennard scaling, Moore's law is slowing, so there's this big gap. But I am convinced that this is so powerful, it'll overcome the bad. The good overcomes the bad. Now the ugly. Who knows the ugly? The ugly is you'll never be able to afford it. Because the cost of design is so expensive today that it is absurd to think that you could tailor an architecture in the future on any generation of silicon within the past 10 years and serve it up to a market. It's just simply too expensive to do hardware design today. And ultimately, the cost of hardware design and the fact that it's so expensive and the rate at which it's growing is killing our community. The number one thing we need to work on as a community, the most important problem we need to work on, is how do we reduce the cost of design? If we can't get a hold on the cost of design and reduce that cost, we will die. Because our solutions, which are going to be heteroparallel, will be too expensive to deploy. So here's what I want you to remember out of this talk today. That bridging the Moore's law performance gap is less about how to do it. I know you guys will figure out how to do it. It's more about how much does it cost. If it costs $100 million to get your solution out there, then your solution has to target a market that can serve up many hundreds of millions of dollars of revenue. And that's a very unlikely market for any specialized device. And my claim, what I think is the solution to this problem, is if we can get a 100x reduction in the cost of taking an idea to the market, that's design, verification, manufacturing, and delivery, then innovation will flourish and all these scaling challenges are overcome simply by restarting innovation in our community. So how bad is the cost of design? It's really bad. This is looking at 500 nanometer down to 20 nanometer, and I'm tracking here hardware design and verification, software design and verification, and manufacturing mass costs. In 20 nanometer, which is a lagging technology, that's a previous generation technology, it's estimated $120 million to bring an idea to the market. So if you're a startup, you're going to need probably 3 rounds of funding to bring an idea to the market. Very unlikely scenario in any startup to get 3 rounds of funding. We're talking $45 million for hardware design, or $55 million for hardware design verification, $45 for the software, and $20 million just for the masks, just to produce that custom piece of silicon. That seems really ridiculous, especially when you consider the software world. You see that right there? That's $500,000. What can you do with $500,000 in the software world? Well, for instance, you can make a company like Instagram and deliver your product to the market for $500,000. Instagram is a $35 billion company. It's worth twice as much as NVIDIA, 3 times as much as Xilinx, and 4 times as much as Synopsys. And it was started with $500,000. Good luck trying to start a hardware company with $500,000. You're going to need at least $100 million to start a hardware company. And as a result, there's no innovation in our field. There's no innovation. I talk to CEOs and CTOs of hardware companies, and they don't want my center doing anything that would help produce startups, because they can't remember a time when big companies bought little startups to create technology and to acquire that technology. They can't remember that anymore. Talk to an exec at Microsoft or Google, and it's the exact opposite. They want a flourishing startup community so they can acquire technology, because they know they can't grow all their own technology. Because of this really expensive cost, nanodiversity, the number of designs in the world, is steadily decreasing over time. This is ASIC starts over time. This is the number of unique designs that happened in a particular year. Back in the late 90s, there were about 10,000 designs per year started. And then with the dot boom, there was a huge drop off, and we've been on a pretty steady decline. Today, we're on roughly a 3% decline per year in new ASIC starts. And we're at about 2,000 in the last year. 2,000 ASIC starts. 2,000. Huge planet, billions of people. 2,000 new designs that people are attempting to take to market. 2,000. It's nothing. How many software startups were there last year? Probably in the millions. All right. So let's say you don't believe me. Maybe Mother Nature can convince you. In biology, there's this theory called the RK selection theory, where R is the number of babies you have, and K is the amount of quality raising you put into those babies. I got a lot of kids, and I can tell you that when you have more kids, you spend less time with them, right? Now, the RK selection theory says that when the environment is unstable, everything around you is changing, the species that produce more babies do better than the species that have less and put more time into their babies. Why? Because with more babies, there's more opportunities that someone's going to adapt to the quickly changing environment. In a stable environment, the K selection species tend to thrive better because they're raised to compete very effectively in a stable environment where everyone's competing for resources very efficiently. So, for example, on the safari, the elephants are very efficient at competing for food, and they raise few babies and train them very well. Well, the analogy here is having babies is like design. That's how nature designs new things, is through procreation. And in unstable environments, we know the rats are going to do great. And in stable environments, we know the elephants are going to do great. What kind of environment is the silicon world today? Is it a stable environment or is it an unstable environment? I would claim it's highly unstable. Costs are changing dramatically. Reliability issues are raising. We're losing Dennard scaling. Extremely unstable. But what kind of designs do we do? If you're sticking $100 million into design, you're really putting some care and love into your child. The kind of design that would be more like our selection would be $500,000 many cheap designs, kind of like they have over in the software world. Much different than what we have. So really, we're like a bunch of elephants in an unstable environment. We're like a bunch of elephants walking into a zombie apocalypse. And it's not going to end well for the elephants. So it's really a bad match. We want to be able to design very cheaply so that we can have many potential solutions to overcome challenges in silicon and reliability and new applications, etc. So let's talk about some, what I would claim are better remedies, places where we need to focus as a community. Now, for me, it's all about accelerating innovation and system innovation. I don't care about microarchitectures anymore. We've done microarchitectures. We've perfected the microarchitecture. There's small tweaks we're going to do, but today it's now about system architecture. How do we take these components that we've built and perfected over many times and compose them together to create better systems? And where we need to create new components is when they're demanded by the applications that they serve. And how do we make it really cheap so that anyone can do it anywhere? Well, anyone, anywhere, with a little bit of resources, not 100 million, but let's say if you had like one rich uncle, you could do a hardware startup. That's the world that I would like to see. And I think that world would be a dramatic change for all of the problems we have in hardware design. So I've got 5 proposals on things we can do. One is we need to expect more from architecture. I'll have a slide on each of these. 2, we got to reduce the cost of designing custom hardware. 3, we need to embrace open source. 4, we need to widen the applicability of custom hardware. And 5, we need to reduce the cost of hardware manufacturing. Now, most architects go, hardware manufacturing? What do I have to do with that? I'm going to show you that I think the key to reducing the cost of hardware manufacturing doesn't come from the technology side, it comes from the architecture side. All right, expect more from architectural innovation. One of the ways we're going to get back and close the gap, the Moore's Law gap, is by just doing better as architects. I grew up in a time when if you wanted to get an ISCA paper, you needed to have 15% and you could get an ISCA paper. I remember people quoting the 15%. You got to have 15% speed up. It's going to be tough to close that 10x with 15%. It's even more tough if you're at Intel. At Intel, they always taught us, I need 1% speed up for 1% area. Oh my gosh. That's a long way to get that 10x out of 1%. Now, why did they want this rule? It's because it allowed performance to track density changes, right? Perfect. 1%, 1%. Since I started CFAR, I've been saying to everybody, your idea has to deliver 2x or more, or let somebody else pay for it. You can do that work, just don't do that in my center. And I've really seen a dramatic shift where now I have lots and lots of ideas that are up there beyond the 2x. And let me show you a couple. Here's one of my favorite ones. This is from David Brooks at Harvard. This is the HELIX-UP work. It appeared in HPCA about a year ago. Now, I love this work because this is a compiler optimization that provides 2x. In the hardware world, we have something called Moore's Law. We expect density and traditionally performance to scale at a rate of 2x every 18 months. In the compiler world, they have what's called Probstein's law, which says that the performance of a compiled program will double with compiler technology every 18 years. They don't expect a lot from the compiler in terms of performance. But here's a way you can get your compiler to give you a 2x. This is a parallelizing compiler, this HELIX-UP compiler. It takes a serial program and decomposes it into threads. One of the challenges there is trying to find where are all the dependencies between these threads at compile time. So what this does is it does profiling of that. It tries to find where there's no dependencies between possible points in the program, as many other parallelizing compilers do. And then it does one other thing that other parallelizing compilers have not yet done. It tries to eliminate dependencies that it sees and then looks at the impact it has on the quality of the output of the program. So the question it's asking is, are there dependencies which are slowing my program, but when I eliminate them, they have minimal impact on the correctness of the result? And the answer is there are a number of dependencies that do exist, and when you eliminate them, you get roughly a 2x speed up over parallelizing compilers. And you get about a 4% reduction in the quality of the output. So if you sort of set that bar higher, people will do more dramatic things and generate more understanding on how to do scalability through innovation. Here's some other work that's by Kevin Skadron at University of Virginia, where he wants to do efficient data mining algorithms, and he's doing that by integrating them onto a DRAM chip. So he gets massive parallelism, and he reduces the latency of accessing his very large data sets. He does this by working with Micron. They integrated finite state automatons into the row buffers of a DRAM, and they compute with those FSMs to implement these data mining algorithms. They get 90x over a CPU, but they get 2x and greater over the best known algorithms on CMPs and GPUs. And so projects like this have seen a resurgence again in near memory computing. There's another opportunity to provide a lot of value there. The second recommendation I have is let's reduce the cost to design custom hardware. And that's really all about high-level synthesis, which is a technology that's been around for a long time. But now we got to get serious about it. Serious in the sense that we invest in high-level synthesis, serious in the sense that architects start using high-level synthesis. Here's an example of a project that's getting traction on both sides. This is the ALADDIN project, again from David Brooks at Harvard, where he'll take C code descriptions of the algorithms combined with a variety of architectural constraints that this particular accelerator has to live under, and then this will do a design space search analysis to find the Pareto optimal designs under those constraints. It does almost as good as hand-built designs, and very soon these technologies will surpass what humans can do, just like that happened in the compiler world. In addition to this, you're also going to need, if you want to design effectively and inexpensively, we're going to need good benchmarks to help us understand what are tomorrow's killer applications. And a great example of this is the Cortex suite from Mike Taylor at UC San Diego. The Cortex suite brings together a lot of next generation algorithms you normally associate with humans doing by hand. These are starting to move into future next generation algorithms, things like learning and selection, language processing, computer vision, computational photography, a variety of very cool and next generation algorithms. Michael's doing a really great job maintaining this, both in that he tries to make it as simple as possible to allow people to refactor these codes and to wrangle them in a way that it works well with your particular designs, as well as keeping it evergreen. In the last 2 years, he's added 4 new algorithms to this suite, and he'll continue to keep this evergreen. A really great benchmark suite I recommend people take a look at. The third thing I want to encourage our community to do is to start thinking seriously about embracing open source concepts. We need to have hardware IP that is free. When I talk to my colleagues in industry, this is really an anathema to what they see as the future of computing. They want their IP to be locked down and sold, and that's how we're going to make our money selling IP. Well, what I want to tell you is that a successful design community is more sophisticated than that. It says that there's a line in the sand where everything behind that line is stuff that we don't have to pay for anymore. Why do we have to pay for a USB 3.0 interface in hardware? I mean, that's old technology that everybody spends money again and again on perfecting. Why can't we just have one that we built and share, and if we want to do changes to that, we can do that? So we need to have a line where everything below that line is free, everything above that line is advancements and deserves to be paid for. This is what they do in the software world. And it works really well for them. You can build a lot of infrastructure starting with significant amount of free and open source intellectual property. Okay, so let's just do a little thought experiment to see how bad things are in the hardware world today compared to the software world. Let's say you want to build the next great smartphone. you're going to need an SoC, hardware SoC, and then on that hardware SoC, you're going to need software to run on it. Okay, so what are we going to do? We're going to build our hardware SoC. This is my big hardware SoC. I've got some I got a couple ARM CPUs in here. I've got a video coder, decoder. I've got a graphics GPU in there. I've got some audio processing. I've got some encryption. I've got some screen drivers in there as well. So now what I'm going to do here is I'm going to mark everything that we need to build from scratch or purchase from another vendor in red, and everything that's free and open source in green. So let's see that. Okay, so let's see. Yeah, everything we got to pay for or build ourselves. Right? Everything. There's nothing. We value no IP as free. None. Zero. Zero. Now, when we get done with this SoC, we're going to slap some software on it. And so let's use Android. That's a really popular target. So Android has applications, the application framework, the libraries, the runtime, the Linux kernel. All right, now let's see, what do we have to build ourselves? Well, we're going to have to build a couple drivers for stuff that's specialized on our board. And we're going to have to put that special sauce on there, like maybe we've got our own storefront, or we've got our own, we're selling into the government market, we've got our own encryption on the internet, or whatever. There's some little special something you might add there. And let's see what's free. Oh, massive amounts, millions and millions of hours of effort into this IP. Free, shared. Everyone contributes. It's below the line. We don't have to pay for mail tools. We don't have to pay for kernels. We don't have to pay for Java runtimes. We don't have to pay for Java just-in-time compilers. It's all free. We're building on top of that and creating IP on top of that. Hardware needs to move into that world. We need to decide what needs to be free and what doesn't need to be free. We need to at least ask that question. And there are people doing this. Open source hardware is growing. We've got the Arduino. Now it's open source in sort of the system level sense, but it's gained a lot of traction having that open, free definition that people can build to and compete to sell you. We even have open source architectures like the OR RISC. The OR RISC, unfortunately, it's GPL'd. And companies hate the GPL. They're afraid of it because it has this copyleft provision where anything that it touches could potentially be under that same license. So I think that license in particular has really hurt the adoptability of the OR, the open RISC architecture. From Berkeley, there's the RISC-V, which is supported. Krista is supported by CFAR. Krista Azanovich is part of CFAR. And this is a open source free architecture. The instruction set is open source and free, as well as a variety of its implementations, Linux port, GCC compiler port, etc. And I've got a lot of hope for this technology. And this technology is really seriously being considered by a lot of upstarts in the hardware business, like China and India. They've done a lot to invest in this. And so there is some hope that we may have some free and open source infrastructure in the hardware world. I think we definitely do need it. 4, we need to widen the applicability of customized hardware. And that seems like a conundrum, right? How do we make something custom that we can reuse over and over and over again? Well, we've already seen this in the world today, things like GPUs. Originally, GPUs were GPUs, targeted at graphics. And then some very brilliant person said, hey, why don't we make it a GPU and target linear algebra? Now all of a sudden it makes sense using this over very wide domains. And the trick there is moving from application to algorithm. And that's the key to widen the applicability of customized architectures. This is Krista Azanovich project at Berkeley called ESP, Ensembles of Specialized Processors, where they take applications and then using compiler tools, identify the computational patterns. What are the algorithms that are inside of these codes? And then map those algorithms to a set of computational resources that don't target a specific application, but target application classes. Things like dense linear algebra, sparse linear algebra, graph analysis, ILP extraction, homogeneous parallel architecture, whatever. They have at this point identified 17 application classes that cover a very broad set of applications. With this, there's a hope of putting an upper bound on the number of accelerators we need, and so now design doesn't require creating these individual components, but again, allows us to focus on how many of the components do we need, how do we compose them together, how do they communicate, how do we manage storage, and how do we map software efficiently to those components. And then we're back to cheaper hardware design. But one of the great challenges with hardware design is you always end up going to the fab, right? And when you go to the fab, they're going to want $20 million to produce the masks for your 20 nanometer chip. So how do you get out of that? And I think the key there is we need to give silicon its personality, not in the fab, but in the assembly plant. Martha Kim from Columbia, her thesis was on this topic. I worked with her on this. She created what she called brick and mortar silicon. Brick and mortar silicon is a form of silicon design where the way you create your design is you purchase components in silicon form, you place them on a two-dimensional surface. So for example, I've got a CPU, a memory block, I've got an FPGA block, I've got a DSP, a specialized graph processor, etc. These components are delivered not only as hardware, physical hardware, they're also delivered with software as well. These are mature components. And then I, in the third dimension, create a polymorphic interconnect which allows them to efficiently communicate with each other. Now what you end up with here is you end up with something that's about 10% slower than an ASIC. But you didn't have to design all this stuff. And you were able to purchase this and put it together without ever even talking to a fab. You're just doing assembly. You've got some robotic capability or you farm it out to someone that does. And you've built yourself a custom piece of silicon that's pretty close to what you could have done with an ASIC at a minuscule fraction of the cost. Now, how do we get over those huge $20 million fab costs? Well, those are paid for by whoever designed these individual components. And they can amortize that $20 million not across just this design, but across any design in the world that utilizes that component. And you create a market for competition on components. Who has the best graph processor? Which one is most energy efficient? That's the one I want to integrate into my particular design. And so in this world, you're creating value in the form of system architecture using components that are really defined by, on this previous page, what the architecture saw as what are the composable components that allow us to build the maximum number of applications. And then if there's something that you just don't know how to build, you can throw your FPGA block on there, or you can go full custom and pay your mask costs. It's a really different approach to design that will significantly reduce the cost of design. Now, fortunately, we're already starting to see technologies that enable this. Interposers, 3D integration. The problem is those technologies today are very boutique technologies. They're expensive. They're unreliable. And so one of the areas we need to do investment in is how do we make those technologies reliable? How do we make them inexpensive? And I fully believe that architects can do that. No problem. So to conclude, here's the problem, right? We've got this Moore's Law scaling gap that exists because we're not innovating effectively to close it. And two, we've got this dark silicon problem, lack of instruction level parallelism, and transistors aren't getting any faster because Dennard scaling has left us. So, silicon's not helping us much. How do we close that gap? We're going to close that gap with heterogeneous parallel designs, customized parallel architectures. The problem, though, is we can't afford that. In today's world, you can't build a customized architecture and then pay $110 million to bring that to market. You're never going to make your money back. No one's ever going to give you that third round of funding to get to market. We need to figure out how to get to market for $500,000, right? So, well, let's build better designs that are valuable, more valuable. Let's reduce the cost of doing that design. Let's get some open source concepts happening in our community so we don't have to pay for every single piece of silicon again and again for the next 50 years when, we're designing that in 370. There should be stuff that's just plain free. 4, we need to widen the applicability of customization by targeting not applications, but algorithms. And once we do that, we can lower the cost of manufacturing because now we can create modularity at the hardware level and we can compose a system architecture out of cheap physical components. The NREs that are killing us are going to be embedded on those components and they'll be amortized over all the world of systems that might want that particular component. And in the end, you got a good chance to restart nanodiversity. A good chance to create a lot more designs. Those more designs are going to solve the problems of the Moore's Law gap. But also they're going to create more jobs, more companies, and more students. You remember that CS and the CE and the E curves before? Enrollments are steady and slightly dropping. If it's cool to build hardware, if you can make money and do exciting innovation in hardware, students will come back in droves. And so ultimately, what we want to do is not scale our systems. We want to scale innovation. That's what we want to do. So in the end, we don't end up with just two forms of CPU and GPU. We're going to end up with lots of diversity that we can handle. So, any questions? Do you agree?
I agree.
Okay. Thank you.
Isn't dark silicon a bit of a red herring because we've had caches for years, right? And now they're basically dark.
Yeah. Yeah.
And most chips have got half of them.
Right. And I've seen people say that one of the solutions to the dark silicon problem is to grow memory faster than you grow logic. And I'll tell you, that's a real sleepy architecture world, right? If we're just building bigger caches. I think.
No, but I think the memory technology is where the interesting stuff is happening.
But that is not going to contribute to the dark silicon problem, right?
I mean, it's going to be dark, right?
It is dark, yeah.
But
yeah.
It also improves the.
It does. I gave a talk at DARPA a few weeks ago, and there was an Intel exec there, Ian Young, he's the technology VP. And afterwards, he gave his talk, and he basically said Intel is going to solve the dark silicon problem. They're going to restart scalability of power as they shrink devices again through better materials, TFETs, 3.5 TFETs, a couple other things they know are going to be very energy efficient. And you know what? It turns out that if you embrace the ideals in this talk, your goal in life is to produce more efficient architectures. And if you're producing more efficient architectures, then if the dark silicon problem goes away, that just means that you get more and more computation for your efficient little algorithms. You can just go wider for everything you do. So I think that if the dark silicon problem goes away, that's only good for everybody. And then we'll be well positioned to take advantage of it. I don't really see it going away.
All I'm saying is it was a relabeling of something that already happened.
Oh, absolutely. It's a long, yeah. It's good labeling.
I don't think that it's. You're right. It's not going to go away.
It's a good labeling.
Just because the scenario of the operation of the chip, especially if it's a sock, you're not going to be doing the Bluetooth when you're doing Wi-Fi.
Yeah.
Maybe you are, but there are scenarios in which functionality costs the chip.
I do Bluetooth when I'm doing Wi-Fi. I was watching YouTube videos in my car the other day. No, I'm just.
You're not doing Wi-Fi whether you're doing While you were driving, yeah. While you,
What my kid was.
yeah, you was driving.
And I had it on the stereo. Yes.
A very general question. You said one of your visions is to bring down the cost of actually getting your idea into a reality.
Yeah.
Yeah. So, how much of to make that possible? What do you think academia has to do versus what do industry has to do?
Oh, I think it has to. I think it'll almost entirely come from academia. Because I have a board of. I have a science advisory board for CFAR. Is that on? It's all composed of CTOs and high-level people within the companies. And it's very hard for me to communicate this vision to them. They love the idea of fewer competition. I've got a slide, I didn't show you this one, but just the number of companies at each technology node producing that technology node, it drops 2 like Moore's Law. They love the idea of being the last standing, which is really bad because there's no innovation when there's no competition. And so having one fab in the world means that at least from the technology side, everything dies. They might be able to regulate how much they can charge for that resource, but there'll be no need to innovate anymore. You'll have captured the market. So they do like the idea of, on the brick and mortar side, they like the idea of more people wanting to manufacture silicon. That's good for them because Intel knows that in 10 nanometer, they can't produce enough silicon to amortize the cost of the fab. They have to have outside silicon going through that fab, which they naturally will because IBM's gotten out of the market. So now there's people will go looking for places to manufacture their silicon. But on the other hand, they don't like the idea of startups. They don't like the idea of creating technology that makes it easier for small companies to survive, which is just like it seems like it's like. That to me, that mindset seems very prehistoric. I mean, are you guys so convinced you can create every technology you ever need that you're not going to need startups? As a result, and then take the open source stuff. I had a nice conversation with Chris Rowan, the guy that did Tensilica, talking to him about open source at Synopsys, and he thinks it's ridiculous. We're going to make all our money selling IP. And so I tried to explain to him, like if you made a bunch of IP free, stuff that you don't deserve to make money on, because it's too old, and then concentrated on trying to make money on new stuff, they don't get that at all. They're trying to wait out, outlive the other companies until they're the only one that can give IP to the 2 or 3 teams that are still designing. I mean, it's crazy. They just don't get it. That's why, I've been going to the DARPA. I've been going to DARPA a lot, trying to convince them, like you guys need to support this because industry's never going to support this. I wrote a big NSF grant. I did the same thing in my proposal. I talked about how that the will to do this change will not come from industry. It'll definitely come from academia. And it's really our job to look past. I would also recommend people go look at Stephen Forrest's talk on the end of Moore's Law. I think that's a really great talk as well. It's on YouTube. Just look for Forrest and Moore's Law. And he paints an even more dour picture than I do. He thinks it'll pretty much ruin the U.S. economy when Moore's Law stops. 1/3 of our economy is based on Moore's Law. 1/3 of our economy is based on our ability to market electronic goods. And so if we can't create value, then we risk 1/3 of our GNP, which would be a big impact to the U.S. We'd have to start at least 2 more wars and really rape Alaska of all of its oils until the end of time. Imagine what they would do to try and replace that in our economy. It would be really bad. So, yeah, I've been trying to get some economists interested in this problem. I think it's a really interesting problem to work on and to postulate about.
think what's going to happen with fabs is that they're not actually going away quite as fast as maybe you think. It may, in the U.S. they are. Well, look, Samsung's building fabs here.
Yep.
And they basically bought Global Foundries. I know that was through another agent, but
It's interesting. There's Mike Taylor gives a great talk. It's called The Suck of Sock. And he talks about how the number of companies that are doing design, SoC design, is dwindling very quickly, right? So pretty soon Samsung is going to determine what your SoC is. There's only one counter example, one counter trend, and that's nation states. Nation states are the only things that can afford to build fabs anew. So that's China and India, right? Taxing every Indian will give you enough resources to build a fab. Taxing every Chinese citizen will give you enough resources to build a fab. Yeah, and then,
so that'll be the end game. It won't be a for-profit.
the end game is, and once China and India get involved, I mean, there's two traditions of manufacturing that really focus on efficiency and cost efficiency. And the rest of the world is focusing on high margins. It's interesting to compare the way the marketing and protection of IP works in the microprocessor industry to the high-end fashion purses industry, right? It's very similar, right? We don't want people to counterfeit our chips or overproduce because there's such a massive margin on the silicon we're selling that people will overproduce and sell at a fraction of the cost and still make a ton of money. High-end fashion purses, same thing, right? So what do? They put like really expensive zipper handles on them so you can identify them very quickly. What do they do on the microprocessors? They put laser holograms on the outside of the chip so you can identify them very quickly. In a market, in a sort of a captured market where the margins are ridiculous, when China and India come in, it's going to devastate them because they're going to have so much room.
They're already there. Look at Huawei's entry into networking, which is basically
Yeah. Yeah.
And now their smartphones they jumped the largest of any smartphone manufacturer.
But look at my vision here. I love China and India driving those prices down, right? Because I don't care about components anymore. Components is last century's architecture. Future's all about systems, system architecture, and mapping software effectively to that systems architecture, and creating value by composing components in a way that's efficient and cheap. So that means design tools, that means getting applications people to work with architects, and creating new opportunities to sell systems. And this idea is also, it's difficult. When I go to DARPA, they go, well, how does that work? And because they don't remember a time when you could do that, right? There's a few examples from, Samsung SoCs and Intel, parallel processors, there's never been a time in our community where people just took all the components and put them together in different ways and then tried to create new applications for those components. It's never happened in our lifetime just because it was too expensive to do design. If you could embrace technologies like assembly time customization, and if you could perfect composable customization, algorithmic composable customization, then you could see a world where you would have cheap components and you yourself could put those together in a way that would create a significant amount of value in, a really small, like a medical imaging application or in a, augmented reality application. And you wouldn't need millions and millions of dollars, hundreds of millions of dollars to manufacture it. You just need one rich relative and maybe an angel round of funding, and you could get to a place where you could show somebody a piece of hardware that would be super impressive.
So why is it not possible to do something at like 130 nanometer? They've already recouped all their costs of the foundry setup, so theoretically they could withstand a smaller margin and then I could use a rich uncle, slower technology, because obviously there's a trade-off. With any kind of composability, you're going to sacrifice performance, peak performance, right?
Yeah, so that's a good thing to think about. So you're basically saying, what if we could go back 2 or 3 generations?
Yeah.
Now
There's a trade, like there should be a war between losing speed because of performance
Yep.
because of generational sacrifice, or I sacrifice customization.
that's interesting. So what if we went back to say 65,
yeah.
which is here at $50 million to deliver? But your point is that we've refined those technologies. We could probably drive that down quite a bit.
Yeah, because they're bulldozing a lot of those factories. So.
I would still argue, don't do that, right? Because you're still going to be tempted to design your own full custom thing. What we really need to do is, along with this idea that we need to get these costs in tune, I mean, only some of those costs are masked. How do we deal with these costs here? Well, the software costs can be addressed quite a bit with open source. The hardware costs could be addressed with open source, with a market where I could buy components rather than having to build those from whole cloth all by myself. So this idea of modularity, I would still want that to happen if you went back 2 or 3 technologies.
Yeah, and I think that's something I think that you miss here is Instagram. How long has NVIDIA been around? Xilinx been around. How long did it take to create Instagram? The time factor of modularity of other people doing the work is really also a benefit.
Yeah.
It's all not all about money. It's about money and time, which in the end equals money.
Yeah. True. Very true.
It's also about Bob.
Yeah. Anyway, stuff to think about. When you go back and work on your research, think about this kind of stuff. I know a lot of people are moving into the heterogeneous, customized architecture space. It's a very interesting one. I think for every effort we put into designing something for application X, we need to consider, would our time be better spent thinking about how would I build infrastructure that could do what I just did there? Because the reality is we've been doing designs for application X, Y, and Z for the last 50 years. You know, how do we now move to a point where we don't have to do custom components? We don't have to specifically target a custom design to an application, but we can instead do a system architecture that can attack that space very efficiently. Anyway, thank you very much for your attention.